Hey everyone, let's go over Chapter 8, Waves and Water Dynamics. Wind blowing across the surface of the ocean generates most waves. We call this a disturbing force. Okay, so atmospheric circulation transfers about 2% of the energy towards the surface of the ocean, and that's what generates these wind-blown waves. But anytime you have an interface of fluids with different densities, that can also, or their interaction can generate waves as well. So when we have the air-ocean interface, that would be like as if you were on a boat on the surface of the ocean, the atmosphere and the ocean are in contact, that's the interface. Ocean waves are generated, right? You can have atmospheric waves, so giant air masses with different densities kind of making their way in the atmosphere can generate atmospheric waves that affects our day-to-day weather. And then inside of the ocean, so think of below the surface, there are also large masses of ocean water with varying density. And when those masses of ocean water with differences in density interact with one another on their interface, that generates internal waves. And internal waves are associated with, if we go back, remember the Peak line? Okay, so there's a low density superficial or surface water that kind of sits on the surface of the ocean and down to about 100 meters. That's the surface mix zone. That's where most wind-generated waves are created. Below that, then you run into the Peak line. Okay. So here, actually, you have an image right here. You can see this here. So here's the low-density water sitting on top of the higher-density water. Okay. So when you have fluids with different densities, this is their interface of, exchange where one sits on top of another, and this is where internal waves can be created. And that's associated with the Peak line. Remember, that's the ocean layer where you have the rapid changing density with depth. Okay, these waves are huge. Okay, now here are your surface waves generated on the surface of the ocean. These are your internal waves. Internal waves can be really big. They're much larger than surface waves. Think of, the best way to think of internal waves, have you ever seen a desktop ocean where it's kind of like this rectangular kind of pivoting container that contains two liquids, one blue, one white, and it sloshes back and forth and it shows you kind of waves bouncing off back and forth from the surface? Or like a lava lamp. Okay, lava lamp has a number of liquids of different densities with different colors being heated up, and so it kind of moves around within the vessel. That's the interaction. Those are the waves that are created. And some of these internal waves can get as large as 100 meters, which is 330 feet. So think of a wave the size of 33 basketball hoops stacked on top of each other. That's pretty big. Tides or turbidity currents, even large ships passing through certain areas can generate internal waves. And internal waves can be hazardous for submarines. If, say, you have a submarine deep underwater at depth, right? And if it gets swept up by a wave that's kind of passing through that area at that depth, it can actually push the submarine or kind of pull it down to depths and pressures that the submarine can't withstand, and then it gets crushed essentially. And many submarines have been lost in this fashion. Okay. So waves, one of the best ways to think about waves is simply just energy transferring through a medium. Okay, the medium being like a substance, right? And that substance in this case is the ocean. The ocean is a massive area filled with salt water. okay? And energies passing through that medium. That's essentially what a wave is. And the water particles in the ocean are the result, or their motion is the result of transferring that energy to the next particle next to it. And then that energy kind of traverses through the medium as it goes along its way. Okay, so the particles in the ocean, as energy is kind of moving through it, can either move up and down, back and forth, or in an orbital fashion, so like circular fashion around and around. This graph here on the right shows us the kind of global distribution of energy in ocean waves. So these are the different types of ocean waves with varying wave periods. We'll talk about what that is in a second. But most wind generated waves occur within this range, okay? And then this is the average amount of wave energy that's produced per year, essentially. So there are a lot of wind-generated waves that produces the most energy right around here. Tsunamis, earthquake, volcanic landslides, those are waves with much long period times, okay? But they still have, they occur infrequently, but they release a lot of energy, okay, into the ocean water. And then ocean tides are more, I guess, predictable, and they occur at specific times, every 12 to 24 hours, I guess, depending on where you are. But it's either once or twice daily, and these are the two peaks of energy for that type of wave. Okay, here are the principal causes for these different types of waves. Here's the gravitational pull of moon and sun, which we'll talk about in the next lecture, and then really what generates most waves on the surface of the ocean is the wind. Progressive waves oscillate uniformly, and they kind of progress through the water without breaking. There are three types: longitudinal, transverse, and orbital. Longitudinal, the best example of this is compression and expansion, okay? Much like hands clapping or thumping on a table. This transmits energy, and then like when you clap, you're compressing air between your palms of your hands, and then you make that kind of clap sound. And as this type of wave passes through the medium, whether it be air or whether it be the water molecules will compress and expand. A transverse wave, the best way to kind of visualize this one is, imagine you're at the gym and you see one of those guys doing that like rope exercise where it's like tied to the wall and they're like swinging it up and down, screaming loudly. Yeah, that workout is like a transverse wave. So it has this kind of S shape where it makes particles move kind of up and down, okay? And then orbital waves are where water particles move in a circular fashion. So they don't like really travel very far, they just kind of bob up and down, and that's the kind of direction of the water molecules as the wave passes through it. Okay, and that's one thing to understand is that again, thinking waves kind of moving their wind-generated waves moving their way through the ocean, they don't take the water along with it, with that ride. They just kind of transfer that energy to the next water molecule. And so the water molecules found here just kind of move in a circular fashion, and they kind of remain in a similar spot to where they were beforehand. Longitudinal waves, like I said, they're also called push-pull waves. They compress and expand, okay? Think of a coiled spring, or I don't know if you guys know what a slinky is, but a slinky, if you attach it to a wall and gave it like a Hadouken, right, it'll compress and expand, and that would travel along the slinky to the wall and then reflect back to you. Okay, longitudinal waves are pretty cool. They can travel through any medium, solids, liquids, or even gases. Transverse waves, those are the side-to-side workout waves with the rope. Energy travels at right angles to the moving particles. So these only transmit through solids and not through liquids. And then orbital waves, the best example of these are waves on the ocean surface, where you have the orbital circular movement of the water particles. All right, let's go through some wave terminology so you can kind of understand it. Here's a cross-section. This is the ocean's surface, okay? And then this is the ocean at depth, okay? So it's kind of like a little cross-section. The crest of the wave is the top of the wave here. So if you're floating out in the water and then you kind of bob upwards and you feel like the highest peak of a wave that's passing by you, that's the crest. The trough is the lowest part of the wave, that's down here, okay? So this is the crest and this is the trough of the wave. The still water level is kind of like a theoretical level where, as if the ocean had zero energy passing through it, the water would lay still at this level. It's typically halfway between the crest and trough. So it's also called the zero energy level. The wave height is the distance between the crest and the trough. So that would be right here, you can see it here, this distance, wave height, okay, to the crest and from the trough. And then the wavelength is the distance between the one crest all the way to the next crest. That would be the one wavelength, okay? We talked about the still water level. I don't know why it's repeated here. But here, this shows you, see these circles here? This all shows you the orbital path of the water as the wave kind of, as the energy passes through the medium here. And the reason why these orbital circles are larger here is because there's more energy moving those particles closer to the surface. As these water particles move, okay, they'll move the particles below them, or the ones below them also move in that orbital fashion. But if you notice the circles are smaller, that represents the amount of energy diminishes the deeper and deeper you go, okay? And we call this here the wave base. The wave base is essentially the distance from the surface to which water particles are affected by the wave energy. Okay, the steepness of a wave, that's defined as the height of the wave, so from trough to crest, divided by the wavelength. And then there's this magical ratio, the 1/7 ratio, okay? So if the wave steepness is greater than 1/7, so meaning that if the height is larger than 1/7 the wavelength, the wave will break, okay? So you'll have rough seas, and then you'll have a wave that starts to have like white caps at the top of it, okay? Terrible drawing, but those are white caps, I guess, okay? All right, I mentioned the wave period. The wave period, this is in time, or T, that's the time for one wavelength, okay? So crest to crest to pass a fixed point. So think of it as you're anchored on a boat in the open ocean and a wave hits the side of the boat, right? It's the amount of seconds it takes for the next wave crest to strike the boat. Or like if you're at a pier and you're standing on the edge of the pier, could be anywhere. Once a wave strikes the pier, then the next crest of the wave hitting that pier, you could determine the wave period. Okay, and that's important because that lets you know how much, or how you can use that to find out wave speed, and it's also important for, I guess, surfers as well. Care about this kind of information so that they can kind of time to ride the best wave from an incoming swell. Wave frequency is the inverse of the wave period, or 1 over the wave period. That's what the inverse is. And what that essentially means is just asking you, in a fixed amount of time, let's say you say a minute, right? How many wave crests will pass by that fixed location per unit time? In this case, we'll say a minute. So you know, every wave crest that strikes the pier, you count how many times it happens in a certain given unit of time. That's the wave frequency, right? That's how often are waves frequenting your area, essentially. Here are the, this is an explanation of the wave base. Okay, the wave base, which is right here, it's highlighted in green. That's the extent to which the energy from the wave that's moving in this direction interacts with the water molecules in the ocean. So it's a depth from the surface. Okay, and what's pretty cool is that the wave base can be calculated based on the wavelength, right? L is the wavelength, right? So say your wavelength is 10 feet. That means the wave base is 5 feet, okay? That means that wave will interact with particles 5 feet beneath the surface, okay? Beyond 5 feet, below the wave base, those ocean water particles are unaffected, okay? So when waves kind of pass through a given area, the water particles move in a circle. Okay, so it's really just the wave form or the energy that travels forward, and it leaves behind the water molecules as it kind of goes through. And this is best kind of shown via the rubber duckies. Let's say you were taking a bath and you created some, massive waves in your bathtub. The rubber ducky, if you look at its, as it's floating in the water, as a wave kind of passes through it, now the wave moves in this direction, the duck will kind of ride up to the crest of the wave, hit the crest, and then fall back down as the wave continues to move forward. And if you track its path, you can see that it moves in an orbital pattern, much like the water molecules that are interacting with that wave. So the wave energy advances and moves forward. Ultimately, many waves, as you well know, because most of us, whenever we go to the ocean, we don't actually go way out into the open ocean. We're either in the coastal waters or on the beach. That's where the wave energy is dispersed, is when waves crash onto land. Okay, so there's the wave base. That's the orbital movement of the water particles stop. And so if you have water depth that is greater than the wave base, okay, so remember, say you have a 10-foot, a wave with 10 feet wavelength, right, which means its wave base is 5 feet, okay, so if you're in very shallow water, right, and if it's deeper than 5 feet, then that wave would be considered a deep water wave, okay, because that wave is passing through the ocean and not affecting or not being affected by the friction of the bottom of the sea floor. So we refer to those as deep water waves. All right, so all wind-generated waves in the open ocean are deep water waves. Why? Because our ocean is very deep on average, and the energy that's kind of moving air masses above the ocean cannot transfer enough energy into the ocean to create shallow water waves. Shallow water waves are the other type of waves. So essentially all wind generated waves, even if it's like a Category 5 hurricane, blowing winds, whipping winds back and forth through a huge area, if it's in the open ocean, it's going to be a deep water wave where there's negligible water movement below half the wavelength of the waves being generated. Okay, the wave speed, which in this case should be called celerity, which is used with the C indication. That is the wavelength divided by the wave period. Okay, and you can use this really handy dandy chart to determine the celerity of a wave if you know essentially just one thing, if you know the wavelength. Okay, so this line here are the wave periods in seconds. Now this is in ideal situations in the open ocean, so if you're in coastal waters, it may not make the same because coastal waters are shallower, so those waves might interact with the ocean bottom and actually slow down, so it's not the same. But if you're in the open ocean, and if you're able to calculate the wavelength in meters, let's say you calculated 100 meters, so you just draw a straight line up until it intersects this graph here. And so the wave period is 8. And because the wave period is 8, you can now draw a line straight across this graph and calculate the wave speed in meters per second. So somewhere around 12 or 13 meters per second with a wavelength of 100 meters. And that's true for anything. You just go straight up where it intersects and you go across, and that's the wave speed in meters per second. Shallow water waves, on the other hand, this is when the wave depth, or D, is less than 1/20th the wave length. So essentially what's happening here is the quote-unquote water feels the sea floor. Okay, so these are big waves that kind of will pass through the entire depth of the ocean. And under those circumstances, to calculate the celerity or velocity of the wave, we use a different equation. Okay, so that's shown here. But this shows you how shallow water waves interact with ocean water. Notice that these are orbital paths of the water, but notice that they're kind of flattened downwards. And that's because of the interaction of these water molecules with the ocean floor. So essentially the ocean floor interferes with the orbital motion, and it causes them to be flattened. Okay. So some shallow water waves, that would be the case for wind-generated waves in shallow areas. Okay, tsunamis. Okay, are tides, and then those are examples of shallow water waves that would make, as they kind of move through areas of the ocean, they would interact with the water that way. Okay, so how are wind-generated waves developed? Well, they initially start off as capillary waves. Think of you're holding, let's say, your morning cup of coffee, and it's a little too hot, so you blow on the surface to cool it down a bit. You're essentially creating wind-generated capillary waves in your coffee. Okay, so the wind generates stress on the sea surface, and I'll show you in the next image, but you create V-shaped troughs, okay, low-lying areas of the wave, and the wavelengths are really small, okay, less than 1.74 centimeters, okay, that's like 0.7 inches, so smaller than an inch. Okay, once, like say the wind continues to blow stronger and stronger and for longer periods of time, these capillary waves their wavelengths, more and more energy will be transferred to these small waves that they'll get larger, and then they become gravity waves. Okay, so once the wavelength exceeds 1.74 centimeters, then you have increased wave energy, and now you get pointed crests, and then the rounded troughs. Instead of the V-shaped troughs like this, you get the rounded troughs. Okay, so here's an image showing you the area where you have capillary waves. But if you have wind continually blows for longer periods of time, transferring that energy, then you'll get gravity waves. And the reason why they're called gravity waves is because, see, if I were to draw the still water level, I know that's hard to do because these waves are kind of small. So what happens is the water, or as the wave's traveling through the water, it hits a height that's high enough that when the wave kind of comes down to its trough, it passes the still water level, and gravity aids in that because the force of gravity pulls that water downwards, and it pulls it past the still water level, and then it adds energy to it so that the wave continues to move forward, or the waveform continues to move forward. So that's why it's called the gravity wave, because gravity is kind of aiding in the kind of transfer of this energy through the water. Okay, so yeah, think of capillary waves as ripples in a pond. You just kind of throw a pebble into a pond, and you see ripples kind of just radiate outwards. Okay. And then when we refer to as the sea, there's a lot of meanings to this, but the sea is an area where wind-driven waves are generated. So out in the open ocean, we've got prevailing winds like the trade winds or the westerlies or the polar easterlies, right? Those prevailing winds are blowing across the surface of the ocean. That's where wind-driven waves would be generated. And that area is also called a sea area. Okay. So some of the factors that affect wave energy, obviously wind speed, right? If you have higher velocity winds, that's more and more energy that's going to be transferred to the surface of the ocean, generating those waves. If you have wind duration that's long, meaning like prevailing winds or sustained winds at high velocities, that's going to even add more energy to the surface of the ocean. And then the fetch, that's defined as the distance over which the wind blows. Okay, so in this image here, this is a storm, so we've got something atmospheric going on here. The prevailing winds are blowing in this direction. Okay, the fetch is the area in which those sustained winds at high velocity are blowing over the sea, right? And that is critical in terms of developing really strong waves. Okay, and so a lot of times with storms like this, a lot of the larger high energy waves move faster than the storm itself. So the waves begin to advance ahead of the storm, and that creates a swell. Okay, and that's where you see this here. All these longer wavelength waves moving ahead of a storm, and that's what creates a swell. And that's why surfers like, a lot of times, especially here in Florida, when there's an approaching hurricane or a low pressure system or some sort of storm, surfers often will go to the ocean like half a day or a day before the storm arrives, because that's when the increased or larger waves will be arriving on the coastline. It's kind of an indication of a storm coming. So they like to surf that, especially here in Florida, because a lot of the waves here aren't surfable, let's say. So when there is a storm, there's added energy, so it makes for better waves. Okay, the wave height is directly related to the wave energy, meaning that if you have like taller waves, obviously then you'll have more energy associated with that wave front. But most waves are typically less than about 2 meters, which is 6.6 feet. But if they break, if you see waves break, especially in the open ocean, we call those whitecaps. And that's when those when they break, that means the wave steepness has exceeded 1/7 the wave height versus the wave length. Okay, that's typically when you'd see whitecaps. Then there's the Beaufort wind scale, and that describes what the appearance of the sea surface would be like in situations where you have a storm or a lot of wind blowing. In page 258 of your book, they show you with pictures what hurricane wind speed and the open ocean would look like if you were out there. This is a satellite image of wave heights globally. And if you look at blue areas or purple areas, these are areas with wave heights that are kind of small. Okay, so you can see that all here, Pacific Ocean, close to the equator. Wave heights in the red here are in 5 to 6 meters. Okay, so those are really big waves, and so you can see that over here. And if you notice in the southern hemisphere, we've talked about this area before, the circumpolar currents. Remember, there's not much land down at these latitudes in the southern hemisphere. This is the area here where there's some land at these latitudes, but these currents kind of encircle the entire globe unimpeded, so they can just keep going, and there's prevailing westerlies that blow in this direction, so that contributes to the kind of really high wave heights here. So these are really dangerous areas to be in the open ocean at these latitudes. Here's the Beaufort wind scale. You can see that in your book as well. It actually has pictures in the book, which is very helpful. Well, you can reference that in case you wanted to see what being in the open ocean would be like if you're under hurricane conditions. So with wind speed in excess of 73 miles an hour, sustained winds. The air would be filled with foam and spray, sea completely white, and driving spray, visibility greatly reduced. You don't want to be out in the middle of the ocean during a storm. Okay, so there used to be kind of a theoretical maximum to what scientists used to think the largest waves could possibly be. And they thought that waves couldn't exceed 60 feet. Although that 60-foot rule was kind of proved wrong by the USS Ramapo. Okay, in 1933 they observed out in the open ocean a 500-foot approximately that long ship caught waves that are estimated that it had been through waves that were 112 feet high, so almost twice that 60-foot rule, which is incredible. The way they measured that was the captains at the bridge of the ship, their eye level was right at the crest of this wave. And so they knew that the bridge down towards the trough or the stern of the ship was about 112 feet. So that kind of proved a lot of people wrong about that 60-foot rule. And the reason for this is because certain areas of the ocean have these enormous waves because of special conditions, kind of like what we see in the Southern Ocean in the Southern Hemisphere. And what that kind of leads to is the understanding of a fully developed sea. Okay, that's an area of the ocean where, for a given wind speed, it's the minimum amount of fetch and duration of the wind where the waves cannot grow any larger, essentially. This is a picture of the USS Ramapo after it had gone through this rough sea, which was actually, it was a typhoon in the Pacific. And this is an aircraft carrier. So this is reinforced steel that was bent downwards. I'm sorry, this is not the USS Ramapo. The USS Ramapo was undamaged. Other ones like this is the Bennington in 1945. This went through a typhoon, and this is the damage from it. So the ocean, those waves and the energy passing through the ocean can be extremely strong. And what's really crazy is that in the ocean, approximately 10 large ships, like container ships or big tanker ships, are lost at sea without a trace. Every year, about 10, just boom, disappeared. A combination of the ocean being so big and inaccessible, as these ships are so far away from being able to communicate with anybody, but the fact that the ocean can have storms and waves, and waves generate not necessarily when there are major storms, but that just can completely overtake a really large craft, which is pretty crazy. So here's that fully developed sea term that I was talking about. It essentially is waves can't grow any further in a fully developed sea because they'll lose as much energy braking. They'll pass that 1/7 rule and get too high up, and they'll start white capping under the force of gravity, and so they can't grow any further. So it's really like an equilibrium condition. And when you have a storm or a fully developed sea, out in front of it, you'll generate a swell. Those are uniform or symmetrical waves that travel outward in front of a stormy area. And the waves that move through here have the fastest velocity, so they have really long wavelengths and long crests. And that helps transport energy from the storm and the prevailing winds out long distances to areas that are unaffected by the storm, at least temporarily. Okay. Here are the different variables for a fully developed sea. Essentially, it's showing you the different conditions necessary to create a fully developed sea, which is something you don't want to be into. If you were on a cruise ship or any other vessel, you would not want to be in an area that has become a fully developed sea where the waves are at their maximum height. So these are the different conditions: increasing wind speed, increasing fetch, the duration of the wind speed, the average height of the waves itself, and the wave period. Okay, swells. So they're longer wavelengths. Those waves travel faster and outdistance other waves. So typically with a storm, you'll have a swell arrive on the coastline with waves with really long wavelengths. Okay, so the frequency is a little bit longer, like so fewer waves hit a fixed point at a certain amount of time. And then once the swell passes and the storm arrives, you get more of choppy wave action. All right, and swells are usually created by what we refer to as a wave train. Now this is an ideal scenario as if a swell was moving an undisturbed sea, but what a wave train is essentially a group of waves with similar characteristics, and they're moving in the same direction. And so what happens is, as the wave train moves into an undisturbed area of the ocean, the initial wave will die out. The leading wave, we'll call it wave 1, will die out, and then wave 2 becomes the leading wave, but then a new wave behind it will form. Okay, and so obviously this is energy being transferred into an energy-less area of an undisturbed ocean. So there's a little bit of energy loss and drop in velocity as the wave train kind of moves through the undisturbed area. But it's an interesting way of how waves kind of travel through the ocean and create an ocean that's disturbed and full of energy when it didn't have any. Okay, so basically the waves are dispersing that energy as they're moving through. Okay, and then the decay distance is the distance over which waves can change from choppy to a uniform swell. Okay, so what happens is the wave train speed is slower, half the speed of one of the individual leading waves. So here it is. This is the wave train. Here's wave 1. So you have 4 waves, okay, moving through an undisturbed part of the ocean. So if you notice, wave 1 dies out, but then behind wave 5, wave 6 emerges. Not as energetic as the first wave, but it emerges, and now you still have 4 waves moving through the area. Wave 2 dies out, and it kind of repeats itself. Okay. This is under ideal conditions. I mean, in the ocean, in reality, if there's a swell kind of moving through an area, there might be another swell moving in an opposite area, so opposite direction, and then some coastal currents that affect the wave trains interacting with one another. So it's a bit more complex. Okay, and that's what leads us to wave interference patterns. This is when you have waves coming in from different directions and how they interact with one another. It's essentially a collision of energy. And when you have 2 or more systems interacting with one another, there's that kind of collision. And you can have 2 things occur, or 3 things really. Well, many things can occur, but these are some of the things. You can have constructive interference, and that's when 2 swells or waves that are in phase kind of run into each other. So they have very similar wavelengths. And so then what happens is, it's this option up here. So you have 2 waves that hit each other and they're in phase. The result is you'll have constructive interference, meaning that the wave heights will get larger and the wavelengths will get larger as well. So this generates stronger wave action when they just happen to be synchronized. Okay. But you can also have destructive interference, and destructive interference are when you have waves that are out of phase and they essentially cancel each other out. So here you go. Here you have this one looks like the wave frequency is a little lower than this one here, right? They're out of phase. So when they collide and interact with one another, they actually cancel each other out, and the ocean becomes calmer as a result. Okay. But in reality, it's not so simple as destructive and constructive. Essentially what's happening is that they're both occurring at the same time. So what you get is a mixed interface. Okay, So what you'll have is waves approaching in phase and out of phase, and every once in a while they'll be in phase, creating a constructive interference in a very large wave, and other times you'll have just choppy waves as they kind of cancel each other out. So we call that mixed interference. And this is what it looks like here. So just imagine here you can see waves coming in at different angles, swells coming in at different angles, and then you get this choppy pattern right here. So here's sea surface height, which is kind of big. It's kind of flat, and then you see kind of big constructive interference, nothing, and then a huge constructive interference wave right there, and then it goes back to the normal over here. So that's mixed interference, where you have two or more swells with different wavelengths kind of moving in. And if you notice, sometimes when these swells kind of move in and the waves are in phase, you'll get a huge change in sea surface height. Okay, we call those rogue waves. Right? Those are massive, mostly spontaneous solitary ocean waves that occur in the open ocean, and they reach really high heights, and they can essentially sink a lot of ships. Going back to 10 tanker or container ships, like those giant ships that carry shipped goods from different parts of the countries for trade. Those are 40-foot containers, and they have hundreds of them on the boat. Those things are lost at sea. About 10 globally disappear without a trace, which is crazy. It makes you think twice about going into the open ocean, because a rogue wave could just occur at any time, even though the odds are pretty low. I think the calculated odds of running into a catastrophic rogue wave are 1 in 1,200. Okay, I'm sorry, 1 in 300,000 running into one of those monstrous rogue waves. And that was the basis of the perfect storm story. I don't know if you saw the movie with was it George Clooney and Marky Mark? Yeah, that's right. Mark Wahlberg, right? That was apparently a rogue wave that sunk their vessel. But other luxury liners like the Michelangelo was damaged in 1966 from these destructive, powerful waves. Here's an image of the Michelangelo, and this crashes through some storm waves in the North Atlantic. You can see the damage that occurred on the ship. It was pretty intense. So rogue waves are really spontaneous and random. They're very difficult to forecast. It's just known by shipping companies and people who navigate out in the open ocean. They know that this can happen. But scientists have kind of narrowed down areas where it's more likely to happen than not. And that means that they can occur near weather fronts or downwind of islands is where they see that these rogue waves occur more often. And if you have strong ocean currents, kind of like the ocean currents we were talking about that are around 40 to 60 degrees latitude in the Southern Ocean, those are areas where you could have rogue waves occur more often. All right, so let's talk about waves in the surf zone. It means waves as they approach land. Okay, the surf zone is the zone where waves are breaking near shore. Okay, the reason why this occurs is because you have shoaling water, and that means that the water becomes gradually more and more shallow as ocean water approaches land, right? So deep water waves, when they encounter shoaling water that's less than half their wavelength, meaning the bottom of their wave base, then they change from deep water waves into transitional waves. And so as waves approach the shore, these are the things that occur. The wave speed decreases, and that's because the water's interacting with the bottom of the sea floor. Okay, the wavelength decreases, kind of like you're compressing an accordion, so to speak, as the wavelength kind of decreases and the waves kind of scrunch up together a little bit. As a result of the interaction with the sea floor, the wave height increases. So the wave kind of grow upwards in height. And when this occurs, then the wave steepness increases. And when the steepness exceeds that magical ratio, 1/7, the wavelength, the wave will break. And you're familiar with this, right? Breaking waves in the surf zone. I'm sure you've been caught up and tumbled around a few times when you've been at the beach. But here it is. So here's the wave base, right? So here's a deep water wave, but then as soon as it starts feeling the bottom, changes start to occur. Okay, so the wave energy or waveform is moving in this direction, orbital paths. But here it starts interacting with the bottom of the seafloor. But if you notice, the water here starts to slow down because of that friction, and then the wave kind of tilts forward. And as it tilts forward, the wave height increases, and as it tilts forward, the wave height increases, steepness increases, and then the wave starts to break. All the while, as soon as it hits the sea floor, the velocity decreases. So that's what happens when waves approach the shoreline. And so that creates three types of breakers: spilling, plunging, and surging. And you get these three different types of ways that waves break based on the sea floor, essentially. Spilling breakers, this is where you have ocean that's gently sloping. And so what happens here, the wave energy is expended over a long distance because it's been interacting with the sea floor. So these just kind of break up and just don't really curl as much. The water slides down the front slope of the wave itself. Not really great for surfing. Plunging breakers are where the seafloor has more steepness to it, moderate steepness. These are ideal for kind of curling waves. So what happens is the wave steepness, it is much higher, and the wave is kind of tilted forward. So then it curls over a pocket of air, and that's when surfers love that, because I got my first tube, bro, because they kind of ride the kind of energy and the waveform as it curls through, and they go through those tubes. So that's best for surfers. You have that curling wave crest, and that wave energy that's approaching the shoreline is expended over shorter distance, and that results in that curving one. Then there's surging breakers, and this happens when you have very steep seafloor, and here the energy is spread over the shortest distance, and you get good body surfing waves because it's very close to shallow water, but not great for surfing because essentially the water crashes into the sand directly. So the waves just break on shore. I'm sure many of you have had experience with this. All right, so surfing is a really crazy sport. I don't do it, but I've seen a lot of surfers on the beaches on the East Coast. West Coast, not as much. But it's really like riding a gravity-operated water sled, so to speak. The surfboard is buoyant, right? So it floats on top of the water. But then you're also kind of riding the force of gravity down the wave, and you're balancing that kind of buoyancy of the surfboard plus the gravity. And surfers, really skilled surfers, can hit speeds of 25 miles an hour, and that's why it's such a thrill. Some really massive waves can be generated. I think in the beginning of the chapter, they talk about an area in Portugal where you see the largest waves form, which under really crazy conditions, once in a generation, man. I'm quoting my inner Point Break here, but the world record holders for that, those crazy surfers will ride waves that are over 80 feet in height, which is insane, because if they fall, they're going to be smashed and pushed around by that water. And many of them actually died or drowned as a result of interacting with water with that much energy in it. Okay, so ever noticed how you've ever been to the beach that the waves kind of crash directly in front of you? There's a reason for that. Waves rarely approach a shore at a 90-degree angle. So what happens is waves approach the shore, they bend. okay, and then they bend until they're nearly parallel to the shore. So when waves approach a coastline, they're rarely like just coming straight at the coastline. They usually come in at an angle, and then a portion of the wave feels the seafloor first, and that slows down that portion of the wave, and so then the other side of the wave moves faster until it also hits the seafloor and it slows down, and so that causes the wave to kind of bend towards the shoreline. Okay, so different segments of the wave travel at different speeds because of that interaction. So here, if you notice, look, the waves are really traveling in this direction, right? And here's where you would be. Woo, I'm hanging out. It's fun. Throw the football around, right? But when you're standing right here, the waves are crashing right in front of you. And the reason is right here, this dashed line is where the waves start touching the seafloor. And as it does, this portion of the wave will slow down, but this portion will speed up as a result. And when that happens, that means it's kind of turning in this direction, right? So these waves kind of slowly turn and then start facing the shoreline. We call that wave refraction. And it just has to do with portions of the wave kind of velocity slowing down. And essentially what happens is the wave starts bending towards the coastline. And so what this means is that wave energy is unevenly distributed along the shoreline. Certain areas of the shoreline will have a lot of wave energy concentrated towards it. Now, I know this is not the case in Florida. We don't have rocky shorelines like this, but say on the west coast of the United States, California, they have a lot of rocky shorelines. And so when waves approach the coastline, these waves will start interacting with the headlands of a coastline first, and then all the wave energy is directed here. It'll cause erosion, break up these rocks, and then the wave energy kind of dies down in these cove areas here, and this is where you see the deposition of sand. So a lot of the coastlines on the west coast will have nice little coves where people can recreationally enjoy the beach, and then these kind of cliffs and headlands that take the brunt of the wave action and storms. Okay. So the take-home message here is more energy is released at the headlands, and then energy is dissipated into the bays. So here's just that angle showing you how waves, incoming waves that are coming in this direction will bend around the coastline and still crash directly in front of you if you were right here. Okay, so these headlands will erode away because they're receiving most of the wave energy, and then over here the wave action dies down, and you actually have a lot of sediment accumulating in these areas. Another cool example of wave refraction, and I've seen this, if you go to New Smyrna Beach, there's a lot of surfers that take advantage of this. We call this the wedge. But in the inlet there's a jetty that kind of sticks out. And so what happens is when you have incoming waves, okay, here's an incoming wave, here's the jetty, right? So that incoming wave will hit the jetty and reflect off of it, and then intersect with the same incoming wave here, and then create larger wave heights in this area here, in this wedge area here. It's wedge shaped, so that's where surfers take advantage of this kind of constructive interference. It's pretty dangerous because look how close they are to the jetty. You don't want to go crashing into those rocks, but this surfer has taken advantage of the increased wave height from this wedge, and it makes it for ideal surfing conditions. Then there are standing waves. This is a different type of wave where two waves with the same wavelength are moving in opposite directions. This can happen in enclosed basins, and particles, let's say in this enclosed basin or like a lake, kind of slosh back and forth. Think of like water in a bathtub. You have a fixed amount of water and it sloshes up and down. So the water particles on each end of the basin will move up and down. Let me show you what that looks like. So here you'll have water move down as kind of all the water moves to the other side of the basin. We call this an antinode. Okay. The node's in the center and it's essentially motionless. So it just kind of swings back and forth like a seesaw. Here's the maximum water flow and then back to motionless. So this just kind of repeats itself as a standing water wave kind of progresses progresses back and forth from each side of the basin. Then there are tsunamis. Tsunamis are incredibly dangerous. These are seismic sea waves. So they originate from earthquakes and sudden seafloor movements of tectonic plates. Earthquakes are the most common cause of tsunamis, but there are other causes. There can be underwater landslides. Remember the continental slope area right off a continental margin. There can be a massive landslide and a lot of debris kind of goes crashing down into the abyssal plain. That can generate a seismic wave. Volcanoes, when they erupt, the edifices are very unstable, and a whole sector of a volcano can collapse into the ocean. That can cause a tsunami. A massive underwater eruption. There's been some major eruptions in the past. Krakatoa, as one example in 1883, generated a massive tsunami from that eruption. And then also meteorite impacts can create large waves as well. So tsunamis occur. Earthquakes are very frequent. Some of these other ones aren't as frequent, but tsunamis can be generated in a number of fashions. But tsunamis have very long wavelengths, over 125 miles, okay? And so they behave as shallow water waves, right? Because if you take half of this distance, which would be, 62 miles, that's way larger than the depth of the deepest parts of the ocean. So these waves, when generated, it encompasses the entire water column and affects all the water in the ocean. If you're in the open ocean and a tsunami passes underneath you, you might not even notice it. It passes very fast. Some speeds are of about 300 miles an hour, and they move through the open ocean. Where tsunamis get dangerous is when they approach the coastline. Okay, so here's an example of the sea floor. We have two tectonic plates kind of moving against each other, and then one of them will move above the other, and one of them kind of moves down. And when this happens, when this whole plate moves upwards, think of it as like you're in a kiddie pool at a community pool, and you're just using your arm and just thrusting huge waves at like a bunch of children that are in the pool, right? And you're just like sending these giant waves to them. That's essentially how they're generated. These giant tectonic plates are just kind of moving forward thousands of kilometers, generating these huge waves. And then the trouble exists once these waves approach a coastline. Okay, so let's say there's like the one in when was it, 2003 in Sumatra. This will generate a wave, and then it'll propagate outwards in all directions, and then that tsunami will hit places surrounding, say, Sri Lanka, Thailand, and cause a lot of damage. They move at really fast speeds. You can fall into the rabbit hole of crazy tsunami destruction on YouTube if you just Google tsunami in Sumatra or in Japan. They have crazy footage of incoming tsunami seismic waves just inundating the area, and it's not like the movies. A lot of times in the movies, it's like this giant wave height, up like 40 stories high. They're huge. They can be up to 40 meters or 131 feet. But most of the time, it's kind of like a sheet of water that comes in and just floods the entire area. So low-lying areas like this would suffer tremendously, loss of life, people drowning because they're getting caught up in this very fast-moving water, hit debris and drown, get swept away, and a lot of loss of property as well. The tsunamis mostly occur in the Pacific, and the reason for this is the Pacific Ring of Fire has a lot of convergent plate boundaries where there's a lot of tectonic plates kind of pushing against each other, and that's what generates tsunamis. In addition to that, there are a lot of volcanoes surrounding these areas, so a lot of earthquakes and volcanoes lead to these catastrophic events, loss of human life. Really, it damages a lot of the coastal areas. Here's an example in Hawaii about $25 million in damage and 159 deaths in 1946 as a result of a tsunami. Krakatau, as I mentioned, was a volcano in Indonesia that erupted and created a absolutely massive tsunami. There was another one in 1946 in Hawaii when there was an earthquake off the Aleutian Trench, which are those volcanic islands kind of off the coast of Alaska. In Papua New Guinea in 1998 there was one. But most notably, and when kind of tsunamis hit the kind of, or were sensationalized by our kind of modern media, was 2004. That's when it was in Sumatra. Let's see. I think I see it here. 2004. Yeah, Box Day. This was the day after Christmas at like 9 a.m. An earthquake hit, and so that's over here. You can't really see. There it is, Sumatra on the other side. But this tsunami propagated outwards and affected India, Southeast Asia, and a lot of people died from this one. Fatalities, 300,000 people. Okay, I don't know if you know, but like the Orlando and greater area has a population of about 280,000. So imagine everyone in the Orlando and cities surrounding Orlando perishing as a result of one catastrophic event, one wave. Well, it was a series of waves. But anyways, a magnitude 9.2 earthquake, one of the strongest in human history, struck this area off the coast of Sumatra. So about 1,200 kilometers of sea floor moved between two tectonic plates. So that basically just pushed a lot of seawater and generated that tsunami. This one was the deadliest one. Coastal villages in this area of the world really suffered because there are a lot of low-lying coastal villages really close to the water. I urge you, I can't do this, but you can watch these YouTube videos to get a sense of what the tsunami destruction was like. Let's see. Okay, so yeah, the tsunami, that Indian Ocean tsunami, the Indian Ocean is also kind of like a smaller ocean in comparison to the Pacific, so you have less time to warn people of an incoming tsunami, but now we have a system of buoys to warn countries after this event, which is pretty crazy. But it traveled more than 5,000 kilometers. Its wavelength was about 300 miles. And an estimation of 230 to 300,000 people died in 11 different countries. Okay, so you can watch that video. So you could spend half an hour watching different crazy videos, but here's just an example of how catastrophic this was. Here's a low-lying area, a town, a before and after satellite image of absolute tropical paradise to nothing there, everything being swept away. It's really tragic. Another notable tsunami was the Tohoku earthquake tsunami, which was March 11th, 2011. Okay, that was a magnitude 9 earthquake off the coast of Japan in the Japan Trench. This one was the most expensive. It affected a lot of Japanese towns. The initial surge was 49 feet, and a lot of these harbor tsunami walls were toppled over. It amplified the local topography. A lot of places were flooded. Watch this video. This shows crazy waves coming into the Japanese coastline and decimating towns. I think here about 20,000 people died. And it also, I don't know if you remember, but the Fukushima nuclear power plant, which is kind of close to the coastline, was inundated by this tsunami, and that caused the reactors to melt down. And then there was a whole issue with radioactivity in the surrounding areas. So it was a big problem in Japan. And they're still slowly cleaning out the Fukushima power plant area from its meltdown in 2011. Still an ongoing issue. But since then, we've developed a pretty good tsunami warning system. The Pacific Tsunami Warning Center in Honolulu, Hawaii uses seismic waves to forecast tsunami. So after an earthquake occurs, they quickly work with the results to try to predict if a tsunami will be generated. But then they have a series of buoys, a system of buoys that's part of the Deep Ocean Assessment and Reporting of Tsunami, or DART. Don't touch my DART. And this detects tsunamis passing through a buoy, and then that way you can warn people in coastal areas of an impending tsunami. Now, the way to get away from a tsunami is essentially just go uphill. You have to get to higher ground, and when you get to higher ground, the water will reach a certain level, and then it'll go back away. I mean, it'll leave your entire village or house completely destroyed, but at least you have your life, right? Most important. But that's the way to get away. And if you're ever vacationing in any areas where there could be a tsunami, one of the telltale signs, obviously if there's an earthquake, if you feel an earthquake, a tsunami could be approaching. Sometimes it could take 5 to 20 to half an hour or a couple of hours, depending on how far away the earthquake was or whatever the variables are. But if there's an earthquake, start to find an evacuation route to go uphill. If you're by the beach and you see the ocean start being drawn out, like it's a really massive low tide, you need to get out there fast, because that means the water is getting kind of pulled out into the ocean, and then it's going to come raging back in. Okay, so this is the Tsunami Watch is issued for areas that when there's an earthquake, then they'll warn people. Here are the buoys, and they can detect seismic tsunami waves kind of passing through the area. So they move ships from the harbors. Most scenarios, you do have a lot of time to prepare for an incoming tsunami. There's only few times where it's a matter of minutes. Okay, but it could be a matter of minutes, so you have to take it seriously. Okay, and finally, waves can be used as a source of energy. There's a lot of energy associated with waves. Essentially, it's just wave energy, waveform moving through the water. So essentially, but there are a lot of challenges to this, because most of the waves that give off a lot of energy or could potentially transfer a lot of energy come from storms. So, it's difficult to protect power plants from the storms. And because storms are not, like sustained or continuous, to produce power consistently could be an issue. Some environmental issues, if you build them too close to the shore, they can interfere with life and also sediment moving up and down the shoreline. Here's an example of one. Okay, so you have incoming wave, and that oscillation of the wave column will push the air in here and make this turbine spin, and that's what generates electricity. So they can be as part of a coastline like this. Again, they're kind of expensive to maintain. They can break down pretty easily because they're getting hit by waves every single day, right? But it's a way of generating renewable energy, so it should be explored. The first commercial wave plant began operating in the year 2000. The Limpet 500, that was a land-installed marine-powered energy transformer off the coast of Scotland, and it generates 500 kilowatts of power under ideal conditions. Right. This one was a wave farm in Portugal, created in 2008, and it essentially just kind of sits here in the water, and it generates about 50 wave power development projects globally with this new idea. So people are exploring this because it's kind of like an endless amount of energy, as just, wind will always kind of blow on the ocean surface, and then that will push waves, and that energy can be transformed into electricity. But here's a global map showing you the ideal areas where a lot of energy could be generated. And, some areas are pretty close to land, so that can be helpful in generating energy. But again, it can be very expensive, and it's sometimes difficult to connect electricity to these distant areas and then efficiently transport that generated electricity to cities that need it.